friends, we were dealing with bipolar junction transistors in our previous videos. Today, we are taking a new direction and starting the topic MOSFET, metal oxide semiconductor field effect transistors. Every electronic devices in the modern day have MOSFET in it. Your modern phones have the CMOS, and the MOSFET concept will help you to understand the working of many modern electronic devices. To start with, we will be dealing a topic called MOS capacitor. Though it is not a transistor, the basic concepts related to MOS capacitors will help us to understand MOSFET in detail. So let's see what a MOS capacitor is. Let's see about the MOS capacitor in detail. The figure on the top shows the basic element of a MOS capacitor. As you can see, let's see more about MOS capacitor in detail. As the figure shows, the top figure is the basic elements of an MOS capacitor. We have a semiconductor, which can be N-type or P-type, which is being topped by an insulator. The insulator could be a silicon dioxide, and which is then connected to a metal which forms metal oxide semiconductor. Metal oxide semiconductor, MOS. The examples of metals that can be connected are aluminum and nickel, and etc. The main aim of studying about MOS capacitor is that what happens to it when a voltage is applied. That is what we will be studying in detail. A voltage that can be applied at the metal side, V, and the other side, the semiconductor side, is connected to the ground through an ohmic contact. Before discussing about that, we will see the band diagram of the MOS, metal oxide semiconductor system. Band diagram. And then we will see what happens when an voltage is applied. Voltage V is applied. We are having two band diagrams. One on the left is corresponding to the N-type semiconductor. If the MOS, the semiconductor in the MOS is the N-type. On the right side we have corresponding to MOS where we are having P-type. And we will be studying the P-type in detail. As convention that we are following, we will be studying one type of MOS which will be helping us to understand even the other type. So one type will be discussed in detail. Now look into the band diagram of the P-type MOS. We have a metal followed by the insulator and the semiconductor. The work function of the metal side is Q phi m. Work function means the work that has to be done to take an electron from the Fermi level to the vacuum level is Q phi m. Then we have the insulator with width d. And on the semiconductor side, we are having the conduction band EC, valence band EV, and the intrinsic level EI, which is the center of the band gap, EG by 2. It is EG by 2 away from EC and EV. And the Fermi level is below the intrinsic level. Because this is a p-type, so the Fermi level will be closer to the valence band. The distance between the Fermi level and the valence band, EF minus EV, is given by Q phi p. And likewise, the distance between EI and EF, how far the Fermi level is below the intrinsic level, EI minus EF, is given by Q psi BP. Q psi BP. If we look into details, we see that the work function at the semiconductor side, which includes Q psi, which is the electron affinity, and also the distance from Fermi level to the conduction band. So the total work function at the metal side, Q phi m, will be equal to the total work function at the semiconductor side, which we will call as Q phi s. This also gives us another indication. So keep in mind that Q phi m is equal to Q phi s. The inference that we get from this equation Q phi m is equal to Q phi s is that the Fermi level and the metal side and the Fermi level and the semiconductor side are aligned at equilibrium, or the two levels, the Fermi level at the metal side and the semiconductor side, are on the same level, Fermi energy level. So this is regarding the band diagram of MOS capacitor, and we have seen the band diagram of p-type in detail. Now let's see what happens when a voltage is applied to the metal. The applied voltage V is known as the gate voltage. The applied voltage V is known as the gate voltage VG. Initially, when we apply a negative voltage, which means Vg is less than 0 at the lead, at the contacts to the metal. What happens is that since a negative voltage is applied, holes will be attracted towards the insulator side, so that there will be an accumulation of holes at the junction between insulator and the semiconductor. And because of this accumulation, the band is being bended upwards. So there will be a bending of energy band on the insulator semiconductor junction. And this type of bending is also known as the accumulation, as holes are being attracted by the applied negative voltage to the junction between insulator and semiconductor. To understand this in more detail, we will consider this diagram. On the top of the diagram, we have three conditions that we will be discussing regarding the p-type. We are having the three different actions happening upon the band diagram based upon the applied Vg, applied voltage. Similarly, by applying the application of different gate voltage in the n-type is also can be explained, but now we will be purely concentrating on the p-type, and that explanation will help you to understand what happens to the band diagram of n-type MOS. As I had mentioned earlier, on application of a negative voltage, we will have accumulation of holes at the junction between the insulator and the semiconductor. And because of this accumulation, the band diagram is bending upwards. And it is also clear from the figure. Now the Fermi level on the metal side and the semiconductor side are not aligned. It was aligned in case of equilibrium condition. At equilibrium, the Fermi level was aligned. Fermi level at the metal side and the semiconductor side was aligned. But here we will see that the Fermi level at the metal side has moved up. And the difference between the Fermi level on the metal side and the semiconductor side is equal to the applied gate voltage Vg. The Fermi level at the metal side and the semiconductor side are not aligned. There is a difference between the level, and that difference is Vg. And this is the accumulation. On application of negative voltage, we have accumulation of holes nearer to the junction. Now, if we apply a smaller positive voltage, Vg is slightly positive. Since we are applying a positive voltage, the holes will be repelled. Electrons in the conduction band will be getting attracted towards the junction between insulator and the semiconductor. The Fermi level at the metal side have moved down when compared to the Fermi level at the semiconductor side. The difference here will be also the applied voltage Vg. This type of action is known as the depletion. So we have seen accumulation and depletion. Here it is called depletion because the holes are being rippled away and there will be a depletion region forming at the junction between the insulator and the semiconductor. Since a depletion region is formed at the junction, this type of bending is called depletion. Now, if we apply a higher positive voltage Vg, what happens? There will be more bending of band diagram at the semiconductor side. Because now we are having a higher positive voltage, more holes will be rippled and more electrons will be accumulated at the junction conduction band, so that the intrinsic level have moved below the Fermi level. In case of p-type, the Fermi level was below intrinsic level. Fermi level was below intrinsic level. On application of the gate voltage, a higher positive gate voltage, we have the Fermi level above intrinsic level, nearer to the junction at insulator, junction between insulator and the semiconductor, so that it is like an N-type semiconductor at the junction, or there is an inversion happening from p-type to n-type at the junction between the insulator and the semiconductor. So this is known as the inversion. Here also, if we see, the Fermi level is at a different level, it's not aligned. The Fermi level at the metal and the semiconductor is not aligned. The difference is the applied gate voltage. The important thing that you have to keep in mind is that on application of higher positive voltage at the gate, the semiconductor is getting inverted. So we are having accumulation, depletion and inversion. Same thing can be discussed for N-type, which we are not going to do because this is, the action is similar to that of P-type. Only thing is that the applied gate voltage is the opposite order. In case of accumulation, we are having a positive voltage applied at the gate in case of N-type. And on applying negative voltages, we have the depletion and the inversion. Now let's see the inversion of the P-type silicon in more detail. As you know now, on application of a higher gate voltage, positive gate voltage, we have an inversion happening nearer to the junction between insulator and semiconductor. The bending is happening downwards and we have the intrinsic level moving down EF, which causes the inversion. A strong inversion is where we have the same distance of EI minus EF on the P side, a similar difference is being formed in the EF minus EI nearer to the junction. That type of inversion is known as strong inversion. In case of strong inversion, we have an N-type formed nearer to the junction with a P-type background. If it was a weak inversion, the band would have been bended such a way that the EI becomes the same level as that of EF, and only few electrons being accumulated nearer to the junction. That is the weak inversion. In case of strong inversion, more electrons will be accumulated at the junction, and the semiconductor gets inverted nearer to the junction. We have WD, which is a depletion width where the bending is happening. That distance is termed as WD. With this, we will wind up our discussion on band diagram, and in our next session we will see a voltage capacitance graph, and mathematically we will represent the same idea of bending. The band bending will be mathematically expressed to the VC, the voltage capacitance characteristics. So in a nutshell, on application of at equilibrium, we have the Fermi level on the metal side and the semiconductor side aligned. This forms a capacitor because it is in the same shape of a capacitor. Capacitor had a metal and dielectric and a metal. Here the only difference is that on the place of metal we are having a semiconductor, and because of that there will be a depletion layer forming between the insulator and the semiconductor. That is what we had seen by the application of different voltages as